In this video, I'm going to discuss Lewis acids and Lewis bases. And a Lewis acid and a Lewis base, it's just another definition for an acid or a base. Just like we had the Bronsted-Lowry, Lewis is just another way to define what an acid and what a base is. So a Lewis acid is going to be defined as an electron pair acceptor. And a Lewis base is an electron pair donor. Now the big difference between Bronsted-Lowry and Lewis is that for a Lewis acid or base, you have no hydrogen required. Right? For a Bronsted-Lowry, the definition is proton donor or a proton acceptor. So you have to have necessarily a proton to be considered a Lewis acid or a Lewis base. But as you'll see in a couple examples we'll do, there are compounds that don't have hydrogens on them that if you put it in water, it'll make it more acidic. So the definition of Bronsted-Lowry doesn't work in that case, but the Lewis acid or Lewis base definition does. So here's an example. We got ammonia here, and we're going to react it with hydronium ion. Positive formal charge in that. So what happens here is the lone pair on this nitrogen comes and takes one of the hydrogens on that hydronium ion. So you end up getting NH4 and H2O. So NH4 plus and H2O. In this case, the Lewis base is the ammonia and the Lewis acid is the hydronium. Because the hydronium is accepting an electron pair, right? That being the electron pair, and the Lewis base is donating that electron pair. So notice that if we were going to define this in terms of Bronsted-Lowry, which we could as well, both of these have hydrogens on it, or particularly the acid has a hydrogen on it, this would be the Bronsted-Lowry acid, and this would be the Bronsted-Lowry base. So every Bronsted-Lowry acid is a Lewis acid, and every Bronsted-Lowry base is a Lewis base. It's just the Lewis definition expands beyond just hydrogens. So you don't have to worry about, being confused if something's a Bronsted-Lowry acid. You don't have to be confused whether it's going to be a Lewis acid or Lewis base. It's going to be a Lewis acid. Right? There's never going to be a Bronsted-Lowry acid that's a Lewis base in the same reaction. So I want to run through an example here of a reaction that doesn't involve any hydrogens, but is still an acid-base reaction. So I'm going to react acetone here with aluminum trichloride. So what happens here is the lone pair from the oxygen comes in and attacks the aluminum, and what we get as our product is a complex. Negative formal charge on the aluminum, a positive formal charge on the oxygen. In this case, right, this is the Lewis acid, and that's the Lewis base. The oxygen donates an electron pair, and the aluminum accepts that electron pair. But there's no hydrogens involved here at all. Last case I want to run through is going to be with a metal ion. If you watched the last video on the acidity and basicity of cations and anions, I talked about how metal ions like iron 3 or aluminum 3 are acidic, right? They don't have a hydrogen on them, but they're acidic because they're Lewis acids. So in this example, I've just got iron 3 plus, and I react that with 6 cyanides. So the structure of cyanide is that. So the lone pair from the carbon comes in and bonds with the iron, and what I end up getting here is FeCN6 3 minus. In this case, the iron is the Lewis acid because it's accepting that electron pair from the Lewis base, which is the cyanide. So when determining what the Lewis acid and the Lewis base are, just look at which of them is donating that electron pair, because that's going to be the Lewis base, and which is donating which is accepting that electron pair, and that is the Lewis acid.